Hello everyone, my name is Belma and I'm going to present our paper, P4air Increasing Fairness Among Competing Congestion Control Algorithms. So let's first set the scene. Congestion control algorithms are a key component of transport layer protocols, and over the years there have been many new proposals, each claiming superiority for specific applications or scenarios. Furthermore, new transport protocols such as QUIC enable quick development of new transport features directly from the user space, enabling even more customization and diversity in the future. However, due to this abundance, it has become almost impossible to take the coexistence and interactions of a protocol with all the other ones into account when designing algorithms. As a consequence, even though when designing algorithms, good fairness properties are usually a priority, many papers have shown that multiple fairness issues exist. So this is especially true when the bottleneck links are shared between flows using different congestion control algorithms or flows having different round-trip times, as demonstrated here. So, for example, if you look at classic TCP flows that track the packet loss, we can see that they overpower flows that use congestion control algorithms that also take delay measurements into account by claiming almost all the resources present at the bottleneck. Similarly, even when all the flows present at the bottleneck use the same algorithm, fairness can still be low if flows have different RTTs, as seen here. Just due to these previously mentioned issues, so low fairness on one side and many new algorithm proposals on the other side, in this paper we decided to enforce the fairness from within the network itself. And we want to do this by grouping the flows based on their congestion control algorithm. Thus, we want to make use of the inherently good intra-fairness properties most algorithms are designed with. In addition, we want to do this from within the data plane. So we want to be able to deploy our algorithm on the switch itself. However, to be able to deploy an algorithm on the switch, we have to take the constraints and limitations of the programmable hardware into account. So this usually means that we are restricted on the types of actions that we can apply to packets, as well as on the number of memory accesses. So these limitations are usually imposed to make sure that programmable switches will run at line rate so that there will be no performance degradations independently of the deployed P4 program. So to achieve this goal, we first started by analyzing the interactions of algorithms present in the Linux kernel. So all algorithms continuously probe for resources by increasing their sending rate until they detect congestion. So now this can be detected, for example, in form of packet loss or an increase in the observed RTT, some combination of these two, or an entirely different metric. So we decided to use exactly this metric, so the metric that's used to detect congestion, to divide algorithms into groups. So in this figure, we see our first group, that's the loss-based algorithms. So these are the algorithms that only rely on packet loss. Consequently, they're among the most aggressive algorithms of all the analyzed ones. Second group are algorithms that use an increase in the observed RTT, so the delay as their primary metric. So these are usually among the very proactive algorithms, and they're among the least aggressive of all the analyzed algorithms. Next, we have algorithms that are somewhere in between these, so that use a combination of these two metrics in some way, and we call them here loss delay algorithms. And finally, we have algorithms that don't use the standard additive increase, multiplicative decrease algorithm. Instead, they try to build a model of the network. So now I'm going to go into the main ideas and building blocks behind P4air. If you look at the figure of a typical programmable switch, we can see that it consists of an ingress and an egress pipeline with some packet queuing and scheduling in between. So in the same way, P4air is also split between the ingress and the egress block and consists of three different modules. So the first module is the fingerprinting module that's also split now between the ingress and the egress block. And the main purpose of this module is to group flows based on their congestion control algorithm. So when a new flow is received by the switch, it's initially classified as a short-lived flow, as we see here. So that is a mice flow, a flow that is still in its slow start phase. Next, its RTT is calculated using the packets involved in the three-way handshake. As the next step, P4air tries to determine the end of the slow start phase, and upon detecting it, it reclassifies this flow into one of the long-lived groups that we discussed earlier. So in this case, it reclassifies it into the least aggressive group, so the delay-based group. Finally, for all the long-lived flows, P4air tracks a set of metrics such as the sending rate and queue length and aggregates these metrics per RTT. So we decided to do this since most congestion control algorithms change their behavior each RTT to react to events or lack of these events. So I'm going to explain this on a bit of more details on an example. So if you look at a typical cubic flow at the beginning, the sending rate keeps increasing, and P4air classifies cubic as a mice flow. As this continues, eventually the sending rate reaches its bandwidth delay product, as we see here, and the flow is being reclassified into the long-lived groups, in this case the delay-based group. So now P4air starts tracking two additional metrics. The first metric is aggressiveness. So this metric tracks how fast a queue is being filled. So if the queue length increases, aggressiveness is increased by 1. Otherwise, aggressiveness is reset to 0. The second metric is bandwidth estimation counter. So this metric tracks the patterns of decreasing the sending rate, which is usually used by algorithms to probe for more bandwidth. So if you go back to our example, cubic now enters the congestion avoidance phase and keeps increasing its rate. With it, the queue length increases as well as aggressiveness. And when aggressiveness reaches a certain threshold that we see here, P4air reclassifies this flow as a loss delay flow, where this flow remains until the aggressiveness, so until cubic starts filling the queues again, and the aggressiveness increases, and when aggressiveness reaches this other threshold, this P4air reclassifies this flow into a purely loss group, which is the correct group for cubic, and cubic will remain in this group until its end. Similarly, if you look at the BBR, we see that at the beginning, it also is classified as a mice flow, and its sending rate keeps increasing until it reaches its BDP, when this flow is also classified as a long-lived flow, same as cubic, into the delay-based group, where it remains, so the same way as cubic, until aggressiveness reaches the same threshold, when this flow is reclassified into the loss delay flow. So up until now, this process is identical as cubic. However, due to its periodic patterns of decreasing the sending rate that we see here, the bandwidth estimation counter is increased as well, and upon reaching a threshold, this flow is reclassified as a model-based flow, where it will remain until the end. Now, while explaining these, I mentioned a few thresholds. So these are the parameters that need to be configured and tuned when deploying P4air, and they usually determine the accuracy as well as how fast we detect certain groups. So the speed of fingerprinting. However, if you look at this example, BBR has a periodic pattern. So if the threshold for the bandwidth estimation counter would be increased, it will take longer to detect this flow. However, it eventually will happen. This is, of course, the general idea. More details and design choices can be found in our paper. So now we'll move on to the second P4air module, which is the reallocation module. So this module performs two important tasks. First, it stores the estimated group, and second, it redistributes the queues between groups. So let's first start with the first task. So the decision to queue a packet into a certain queue, so that this packet is processed with other flows that use similar metrics, must be made in the ingress, so before the packet is queued. However, the decision to reclassify the flow can be made in egress, so after the queue stats are known, as we can see here. However, from egress, we can no longer access the ingress register that stores the group. So to solve this, we decided to send all the packets that trigger a group update back to the ingress. And upon reception of these packets, the group registers are updated. Furthermore, the second task of the reallocation module is executed as well. That's the reallocation module algorithm. So this algorithm tries to adapt to the current network state by favoring groups with most flows by assigning more queues to them. Thus, in essence, it tries to make sure that all queues process the same amount of flows. This way, algorithms such as round robin can be used. So more details on reallocation can be found in our paper. Here I'm only going to explain the basic idea on a simple example with just two groups that we see here. So the delay-based and loss delay group. So to classify all flows belonging to the delay-based group together and all flows belonging to the loss delay group together, we must calculate the parameter L1, so the border between these groups. So let's assume now that at some point in time, we receive an update packet that we see here. So this is a short-lived mice flow that was reclassified into the long-lived groups, so the delay-based group. Now to estimate L1, we use a set of counters associated with each long-lived group, CE. So these counters track how many flows need to be added to a group for L1 to change. Thus for each update packet, so each recirculated packet, these counters are decreased or increased depending on the previous and the new group. So in this case, since the new group is the delay-based group, we decrease the algorithm associated with the delay-based group, C1. As the previous group was a short-lived flow, we don't do anything. So now if C1 reaches 0, meaning that no more flows need to be added to the delay-based group for L1 to change, so that this means that all queues that are now assigned to the delay-based group are utilized just right, so they process at least FPQ, which stands for flows per queue, flows. And if C2 is higher than FPQ, meaning that loss delay queues are underutilized. So if delay-based queues are utilized just right, while loss delay queues are underutilized, we will update the parameter L1, as we see here. So at the expenses of the loss delay group, the delay-based group will gain a queue. So if at some point in time another packet is received, in this case this is a delay-based flow that is being reclassified as a loss delay flow. Again, we are trying to determine if parameter L1 needs to be updated. So same as before, we update the counters associated with these groups. So in this case, however, as the new group is the loss delay group, we decrease C2, but we increase C1 because the delay-based group lost a flow while the loss delay group gained a flow. And same as before, if certain conditions are met, that we see here, parameter L1 will be updated. Thus, at the expenses of the delay-based group, the loss delay group will gain a queue. So, of course, this is a simplified version of this algorithm. However, it can be that only uses two groups. However, this can be extended to include more groups, so 4 in our case. In addition, there's certain special cases when we must update all the counters. So, for example, if FPQ changes. So more details on this can be found in our paper. I will not go through all these details here due to time constraints. Finally, the outcome of this reallocation algorithm will be that all queues are assigned to a specific group, as we can see. And that all packets in these queues should now belong to flows using the same congestion control group. So flows that use congestion control algorithms that belong to the same group. Finally, I'm going to go now through the last P4air module, which is the apply action module. So this module enforces fairness among flows processed in the same queue by applying custom actions to flows. So there are two main reasons to do this. First, flows having different RTTs will still overpower each other, and grouping flows just based on their group is not enough. Second, even flows that belong to the same group and have the same RTT don't actually have perfect fairness. So further, in contrast to the standard AQMs, we decided to use different actions for each group to target their specifics. So this has multiple advantages. First, we are able to target the more appropriate measures for very conservative algorithms, for example, delay. Second, and more importantly, we can also target algorithms that don't react to loss at all. Here we can see these two actions. More details can be found in the paper. So we have delay packet, drop packet, and adjust window. Finally, I want to go through some of the most important results we had. So we did our measurements using the Mininet emulation environment and a hardware setup with a Barefoot switch. So details on tuning and many more other results can be found in the paper. Here I'm only going to go through the most interesting ones. So we can compare P4air to a solution that uses no mechanism to enforce fairness, no AQM, and a solution that queues packets into queues based on the hash of the flow identifier, different queues. Furthermore, we tested two versions of P4air. The first one is idle P4air that actually combines the first two modules, so the fingerprinting and relocation, and P4air that combines all three modules. As we can see in this figure, in all the analyzed scenarios, P4air was able to outperform the other solutions, especially when we compare P4air to a solution that distributes the flows based on the hash of the flow identifier. We can see that P4air, so that grouping flows based on their congestion control algorithm, can significantly improve the fairness, so that the good intra-fairness properties of flows can be used to their advantage. If we compare P4air to idle P4air, we can see that if the number of queues is if the number of flows present at the bottleneck is small, the third module apply actions is not actually needed, as the number of flows competing inside the same queue is very small, sometimes equal to 1, and can even decrease the performance. Finally, we are going to zoom in to one of these measurements, so a measurement that had all 4 groups present. So first, if you look at no AQM, we can see 2 distinct groups. So on the right side, we see flows that are overpowering, and we can, so very aggressive flows. And on the left side, we can see flows that are being overpowered. Same for different queues. While it does improve the performance, the flows present inside the same queue are still overpowering each other. Finally, P4air improves this performance, and most of the flows claim around their ideal throughput. Finally, by applying actions, P4air, in comparison to idle P4air, further improves the performance by decreasing the queuing delay as it punishes the most aggressive flows. Finally, we also tested the RTT fairness, and we can see here that P4air can improve the fairness and outperforms the comparison baselines even in these scenarios. However, the performance does decrease with the increase in the difference in RTT between the flows, which we can see on the right side of this figure. Finally, to conclude, in this paper we presented P4air, which is a P4 solution that tries to enforce fairness among different congestion control algorithms by grouping flows that use the same similar congestion control algorithms that target the same metrics together. And we showed that distributing flows to queues based on their congestion control group can significantly improve fairness in network resource utilization. Thank you.